Hello everyone, welcome to our first EESA Tech Talk session. I am Paul Stechik with Northeast Power Systems, also known as NEPSI, N-E-P-S-I. This is our first Tech Talk using YouTube Live with the EESA. So just to give you some background information, YouTube Live events are recorded. You can always go back and watch these videos. Also, if you want to ask questions, you must be signed into YouTube or into Chrome. You must log in to ask questions. There is a chat box. Go to the chat box, ask questions. If you do that during the presentation, we will try to answer those questions during the presentation. There is no limit to the number of people that can sign on to a YouTube Live event, and that is one of the benefits of this event. So today's Tech Talk is about harmonic analysis. Knowing the basics is essential. This is a very basic presentation about harmonic analysis, and really we boil harmonic analysis down to Ohm's Law. Some other things to know. I'm located in Queensbury, New York, which is about 30 minutes north of New York City, so I'm many time zones behind you guys. Behind me here, and I'm going to try to get out of the way, is information to contact people within Australia. Is John Wright Smith. He is with American Superconductor. He is a direct sales contact for NEPSI. NEPSI is owned by American Superconductor. So if you have information that you require, or if you want to ask about harmonic filters or capacitor banks, John Wright Smith is your contact, and he would be a good person for you to call. So his information is above my head there. Sorry, I'm blocking it. So today's presentation, let me just continue with, let me go here. There we go. All right, good. So just some background. NEPSI was formed in 1995. We were purchased by American Superconductor October 1st, 2020. We still operate under the name NEPSI, again, based in Queensbury, New York. Our key products are metal enclosed capacitor banks and harmonic filter banks, 2.4 kV through 38 kV. We build capacitor banks, harmonic filter banks, shunt reactor banks for pulling in reactive power. We also have what's called a hybrid shunt capacitor shunt reactor banks that are very popular in the renewables area, where we sometimes need to consume reactive power because of the large collector systems used within. We have an ActiVAR product, which is an inexpensive way to start very large motors. Sometimes we go up to 48 megavars. Remember that large motors, when they start, especially induction motors, they pull in a lot of reactive power. We can compensate that reactive power with a large capacitor bank. This is a more cost-effective solution when you compare it to, say, a large VFD drive or a large LCI drive. So motors up into that 5,000 or 10,000 horsepower range, and even up from there, this ActiVAR solution is a great way to start those motors using a simpler, less expensive technology. And of course, we have AMSC products, which also now fall under us, which are the DVAR StatCom and the VVO StatCom. Both of these technologies are using IGBT type technology. It's a power electronic device that produces reactive power, both inductive and capacitive. Those systems are very common in the renewables area. So this is an example of a metal closed system. It's a metal closed harmonic filter system. It's a multi-stage harmonic filter system. When you peer into that system, what you see is all switching, all protection, all control. It's a harmonic filter system. And this is the advantage of the metal closed system, is that it contains all switching, protection, control. It's in a compact, fully integrated solution. It's easy to purchase, it's easy to install, it's easy to commission. These are the types of systems that are often purchased as a result of harmonic analysis, which is the topic of today. We sell into all different industries. Harmonic filters are used in just about every industry. Solar, wind, petrochemical, utility, mining, you name it, it's used in those industries. Of course, we want to use capacitor banks when at all possible, because capacitor banks carry a less cost when compared to a harmonic filter. Normally there's a harmonic analysis that is conducted. The results of that harmonic analysis might dictate that a capacitor bank cannot be used because of resonance issues. We'll be talking about that today. And you then install a harmonic filter. So harmonic filters are often installed to prevent resonance, to do filter tuning, and then also to produce reactive power for power factor correction. Maybe before we'll move on for these two first. So metal closed solutions on the left, open air is on the right. And we can see that there's different configurations, but the end result is NEPSI does not produce open air solutions. They take up a lot of space. It's not an integrated solution. It's more complex solution. It's more difficult to install in the substation, and it takes a lot of area. So metal closed solution is what we provide. There's E-house configurations, the one on the right. It looks like a metal closed solution, but it's a lot different. The E-house configuration is a walk-in type cubicle. You walk in there, you can grab components, and everything is pushed into that enclosure. That enclosure must be designed and built according to the local building code standards. And again, we do not build that type of equipment. We only build metal closed. The metal closed solution is a tailored design that has the components laid out in such a way that it's compact, and it allows you to open the doors and remove pieces or components if they need to be removed. So everything is accessible from the front of the enclosure. And before we get on, I'll show you one quick large harmonic filter system here. This is a 75 megavar shunt harmonic filter system built in our factory in Queensbury, New York. So we ship these harmonic filters from our factory into various locations, mines, solar plants, wind, and so on, petrochemical, basically anybody using a lot of reactive power with nonlinear loads. So these systems come fully assembled, ready for interconnection. All switching, protection control is built within, and they're all tested at NEPSI before you leave the factory. In-post tested, partial discharge tested, SFRA tested to confirm tuning points and the characteristic curves of that harmonic filter. So today's presentation is harmonic analysis. Knowing the basics is essential. So oftentimes I meet with engineers, and they talk about harmonics as if it's a mysterious thing. They do not understand harmonics, and it's obvious when you talk to them. So today's presentation is about knowing the basics, and really we boil harmonic analysis down to Ohm's Law, V equals I times R, more or less. And if you follow along for the next, say, 35 minutes, you'll have a very good understanding of harmonic analysis. Our philosophy is that you must be able to do your harmonic analysis on paper, pencil paper, calculator. If you can do it on paper and with the calculator, you can then utilize the programs ETAP, PSCAD, and those programs, those digital analysis programs, to conduct your harmonic analysis. Without knowing the basics, you cannot possibly understand if your results are correct. You need to be able to do paper calculations, back of the envelope calculations to verify your results. So some basic knowledge is necessary. So why perform harmonic analysis? First, you're looking to determine compliance with a harmonic standard. In North America, we're oftentimes talking about IEEE 519. In Australia, you have your own standards. So you're conducting harmonic analysis to determine if your facility, whether it's a renewables plant or a mine, if it's compliant with some harmonic standard. You might be thinking about expanding an existing facility, or you might have an entirely new facility. Harmonic analysis allows you to predict the performance of your system. Do you meet the harmonic standards? You might need to calculate voltage distortion, current distortion. As a rule of thumb, when we do our analysis, our philosophy is to not have greater than 5% voltage distortion within the plant. We're going to operate that plant, and we want to make sure that the power quality is good enough for problem-free operation of your process facility. So voltage distortion, is an important parameter, more important than current distortion within the plant, because voltage distortion determines power quality within your plant. It's what all the loads see. They're connected across the bus bars. We may have to evaluate resonance concerns, another key point. When you install a capacitor bank within a system, you create resonance conditions. We want to make sure that we don't have resonance concerns. When you have resonance, you have high voltage distortion, you have high current distortion, so you therefore have a poor power quality issue. So evaluating resonance is another reason. And then you want to evaluate filter design. Part of harmonic analysis is, I got a problem, I need to fix it, I'm going to evaluate the filter design. It's an iterative process. And really, harmonic analysis, there is not one correct answer. There's many correct answers. But some answers are better than others. Some are more economical than others. Some are not reasonable. Sometimes we look at a harmonic filter design and the result is not reasonable. The design is not reasonable. Oftentimes it takes a lot of experience to know what can be built and what cannot be built. So there's a lot of steps in performing harmonic analysis. All the programs that are out there nowadays, you can do load flow analysis, short circuit analysis, and a package is added on to do harmonic analysis. So much of the same data is used in the harmonic analysis to do load flow as it is in harmonic analysis. Really the key things in a harmonic analysis is you need to know the nonlinear load data, the harmonic current injection data, and then the impedance data of the network. We recommend some kind of validation of the system, of your model. You create a system model, you need to validate that. Validation is best done with load flow, short circuit, but some basic hand calculations is also advisable. So we're going to be talking about those in a few minutes. And then if you've taken measurements within the system, you can certainly compare your harmonic analysis output, the results, with the measurement data. Measure volts and amps within a network. Does that match my model? Run the harmonic analysis and determine if it matches. We're going to talk about impedance scans as an important part of harmonic analysis, interpreting impedance scans. If you've ever seen harmonic study, a lot of times it's full of various impedance scans. So we're going to talk about how to read those and what the significance of those are. Harmonic calculation of current distortion and voltage distortion, another key thing. Remember, we're looking to improve the power quality within the plant, to keep the voltage distortion, say, down below 5%. We're also looking to determine, well, what is the current distortion throughout the plant? We may have to increase the K factor rating, for instance, of a transformer if we have a lot of harmonic current flow. Also, we're looking to calculate current flow also. Filter design is an output of a study. We got a problem. We need to improve the power quality within the plant. We need to do some type of filtering. We need to be compliant with the harmonic standard for the interconnecting utility. So we develop a filter and we verify that filter design. And then finally, a report. And the report is where all the work is done. I mean, there's a lot of time put into developing a report. We have a philosophy here at NEPSI that we like to present the report and not spend so much time in preparing the report. So we don't prepare those doorstop type reports that you commonly see from some engineering firms. So linear loads versus nonlinear loads. The top curve here shows a linear load, and if you put a sinusoidal voltage across a linear load, you'll get a sinusoidal current. In other words, the current matches the voltage. So you apply voltage across a load, you get a current flow through it, they match. One on the bottom, we apply to a nonlinear load, and this might be, say, a power supply to a computer. If we apply a sinusoidal wave to the load of a computer, the actual current wave shape will be a square wave, similar to what you see here. But other loads, such as variable frequency drives, cycle converters, LCI drives, rectifiers, they all have distorted waveforms where the voltage and current do not match. So if I were to ask, well, how do you do that analysis? How can I evaluate the impact of that load on the system? you would have this wave shape here, and it does not follow the standard method of doing network analysis that you learned in college. Because in college we've learned how to work with sinusoids, not with square waves. It's a little bit difficult. So what we do is we take the square wave and we can break it into subcomponents called harmonics. And if you see what I'm doing here, I'm taking that square wave and I'm decomposing it into various sinusoids. And it gets to a point that I can add, let me go back, I can add all these different harmonic currents here and come up with a square wave. So what we're able to do is we're able to take a network and we're able to do standard network analysis, but we got to do it at each and every frequency. We do it at 120 hertz, which is, well, we're going to go with 50 hertz system since we're talking Australia. So the fundamental frequency, remember, is 50 hertz. Second harmonic is 100 hertz. Third harmonic is 150, right? Fourth and so on is 200 hertz. So we're going to create a network model for each and every frequency in the network for each and every harmonic. And harmonics are integer multiples of the fundamental, which is 50 hertz. So we're able to then use standard network analysis that we would have done in college at each and every frequency. So obviously one calculation may involve 50 calculations when you do harmonic analysis. If we're evaluating the harmonic response of a network and we're going to the 50th harmonic, it's going to be 50 sets of calculations that we must do to evaluate the harmonics in that system. So we're going to continue on with this subject matter. And don't forget questions in the chat box. If you ask the questions, we're about 30 seconds ahead of you guys. So if you ask the questions, we'll get them answered. We're going to start with a very basic network here. And let me start off. We have a source impedance here. This would represent the utility interconnect. You're supplying utility. In this case, we have an 8 kA short circuit current. We have a source bus. We have this thing called PCC. This is a concept that's utilized with the IEEE, and it's called the point of common coupling. It's really the interconnect. It's where the harmonic standards are applied for interconnection to a utility grid. If you're, say, a utility a customer, electrical, petrochemical plant, or a mine, for instance, or a renewables plant. We have an input transformer TX1 here, and in this case it's 10 MVA, and it has a 7.5% impedance. And then down here we have just a very simple bus bar, 13.8 kV, and we have some harmonic producing loads. Those harmonic producing loads might be an LCI drive, it might be a VFD drive, it could be rectifiers, it could be wind turbines, solar inverters, you name it, whatever produces harmonics could be that. We've taken all the harmonics within the plant and we've summed it up and put it into one load in this particular model. So if we were to take this standard three-phase network here shown on this one-line diagram, we could create an equivalent network over here consisting of Z T, which is a transformer impedance. It consists of both an X and an R. And then Z of S here, which is a source impedance. It represents the source impedance related here from the utilities based on the short circuit impedance of the network. And that again is represented by the X and the R value here. So in total we have two series impedances here. It's a very simple network. And so remember what we did here, we've taken a three-phase network and we converted it to a single-phase model, and that's what we show here. At the end here we have the harmonic current injection. In general, nonlinear loads are often modeled as harmonic current injections, ideal current sources, and that's what you would typically see. What is the harmonic current injection from an LCI drive? It has a characteristic impedance, and you can take that value and put it into your analysis program at each and every frequency. Here we have taken and we've assumed a value of I5, which means the fifth harmonic, and it's 8.3 amps. I7, 6 amps. I11, 3.8 amps. This analysis I'm doing is all done in amps. Amps, ohms, and volts is not done in per unit. So we have a per unit system, and we have just the standard way of doing it, network analysis. So we can assign some impedance values to it. Let me first go here and note that depending upon a nonlinear load, there's characteristic harmonics for various devices. You might have what's called 6-post, 12-post, 18-post devices, and they have a characteristic harmonic that you can evaluate your load. I don't really have time to get into all the details here, but just know that if it's a rectifier, if it's a cycle converter, if it's a VFD drive that's got a certain post number, there is a characteristic signature of that device. In other words, what harmonic currents it's going to inject in the network. So it's worth noting that you don't necessarily need to have data from the supplier to do harmonic analysis. You can make some assumptions. And if you make those assumptions conservative, you're probably okay. Here we have what's called the point of common coupling. There's oftentimes some type of standard. I'm interconnecting to the utility. There might be a voltage distortion standard. There might be a current distortion standard. Depending upon the country you're located in, that standard is going to change. In this case, I have it based on IEEE standard here. All right, let me see here. Go back. Okay, so we've assigned some impedance values to the source impedance here, and also to the transform impedance here. And we go through those calculations here. And again, it's important that you be able to do it by hand. We go through the method. Okay, I'm going to calculate the source impedance based upon 8 Ka, a 138 kV short circuit, and I get a value of 0.1 ohms. You got to remember that the source impedance, we got to reflect it through the transformer if we're doing the analysis at 13.8, and that's actually what I'm doing. So I reflect that impedance through the transformer. So X of S at 13.8 is 0.1 ohms. We also have to calculate the impedance of the transformer, and we have that here. Remember, the X values and the R values add together. Okay, so you have a complex impedance there. R's and X's add together. You just can't add those numbers together. But this is a very simple series circuit. We can take it and we can combine those impedance values to a single X and a single R, and that's what we've done here. The first thing that's interesting to note is that the resistance is very low. It's only 0.08 ohms. So you could more or less throw that out of the analysis for the back of the envelope calculation. You could throw it out. We will be just left with a single impedance. And obviously it's easy to calculate the voltage here. If I have the 8.3 amps of fifth harmonic current here, I could take that 8.3 amps, multiply times 1.52 ohms, okay? And again, I got to multiply it by 5 there because it's the fifth harmonic. Remember, going back to the previous slide, I didn't take note of it. Here, X of L, the inductive reactance, is equal to 2 pi FL. So if I go up in frequency, say to the fifth harmonic, I got to multiply my fundamental impedance, my fundamental frequency impedance, or X of L at the fundamental frequency, by a factor of 5 because it's at the fifth harmonic. Capacitors, on the other hand, as you go up in frequency, the impedance drops. All right, so you take the 60 or 50 hertz of reactance and divide by 5 if it's a capacitor bank. So it's easy to develop the impedance model for each and every frequency, and that's what we do there. So once we are able to calculate the voltage and current throughout this network, we can then calculate what's called the total harmonic current distortion here, and the total demand distortion, and then finally the total harmonic distortion. So ITHD, ITDD, and VTHD. The difference between THD and TDD is demand distortion is based upon some demand period, normally 15 minutes. What is the maximum demand of a facility over a 15-minute period, and that becomes the denominator for the calculation. Total harmonic distortion is an instantaneous value. What are you getting at this moment? Okay, so it's just putting the fundamental in the denominator, the fundamental frequency at that moment in time, and all the harmonic currents at that moment in time. And so using these calculations, we can come up with those various distortion values. Down here on the lower left is a very simple impedance scan. And if you think about it, as we go up in frequency, the R value doesn't change. It doesn't change based upon frequency. Now, theoretically, remember that there is the skin effect and there's proximity effect. So harmonics do have a small impact on the resistance in cable and of conductors, but the number or the change is small. So for back of the envelope calculations, assume resistance stays the same. And again, you can almost assume that it's negligible here, because at the fifth harmonic, if 0.08 ohms has not changed, it's 5 times 1.52 ohms. It's a lot more impedance. So we get a simple straight line for this circuit, just a simple straight line. As we go up here in harmonic number, we go up linearly with in ohms with harmonic number or with frequency. So it's just a straight line. We can take the values of 8.3 amps here and overlay onto this impedance curve here. So 8.3 amps times that value of ohms at the fifth harmonic, okay, will give me the volts. And that's what I do here, gives me the volts. So 8.3 amps times the value of ohms will give me the volts. And I can do that each and every frequency. And I create a bar chart. VTHD is, in this case, is 1.9%, calculated according to the equation here. So we've already did the most basic harmonic analysis. Very, very simple to do. You're just breaking this problem down into pieces. Let me go back. Okay, I got it covered. Next slide. Say now you add a capacitor bank to the network, and that's what we're doing here. Here's a typical NEPSI metal closed cap bank being installed within the substation, and you say, well, what can happen? What can happen? We put that capacitor here in our model, and we can calculate the impedance of that capacitor at 50 hertz or at 60 hertz. So in this case, 1 megavar is 190.4 ohms, 2 megavars is 93.1, 3 is 63.5, 4 is 47.6. So as we're adding megavars, we're dropping down impedance. Makes sense. Megavars is equal to the voltage squared divided by x of c. So as we increase in megavars, we're dropping the value of x of c to increase in megavars. We create the equivalent circuit again, and in this case, we got the same value at the source, the 1.52 ohms and the 0.08 ohms. But we have this capacitor here now, which is variable based upon the number of steps online. And it's very common that you have multi-stage capacitor banks that have these variable impedance values. So remember, the green curve here represents the capacitive reactance of the circuit, As we go up in frequency, okay, the impedance is going down because it's x of c divided by n, as we show here. And then we have the red line, which represents the impedance of the transformer up here. There's a crossover point. That crossover point we refer to as resonance. For a very simple circuit like this, you can calculate that resonant number here. It's equal to x of c divided by x of l square root. So you take the fundamental value of x of c, fundamental value of x of l, divide those numbers, take the square root, you have the harmonic resonant number, what harmonic it's resonating at. What's important to note here is that this formula only works for this system configuration. If we were to put additional capacitors out here, say at the utility interface or say we were to have a low voltage network and we were to put capacitors there, this formula falls apart. You can't use this formula, and that's really where harmonic analysis gets a little bit more complicated, and you use a program, and that's what we would recommend. So that resonant point, we can calculate that. In this case, it's 5.59. If we were to draw the impedance curve, though, we were to say look into the circuit here. We got the secondary bus. We look into the circuit. What impedance does that harmonic current injection see? Well, that's shown here with that magenta curve. The magenta curve is the impedance, the driving point impedance as it's referred to. So here you can see what has happened. We have that red dashed line here. That's that original transformer impedance line, source impedance line. Okay, that's the starting point of this analysis. What have we done? We have increased the impedance of this network at all harmonics basically less than the 9th harmonic here. You can see we're greater than, which means that if we had current injection, if we take current injection, we're multiplying that value of current times more impedance at each and every harmonic number, resulting in more voltage distortion, and that's what we show here. The voltage distortion now is 4.32%. So it's just marginally acceptable. It's marginally acceptable. We would consider 5% our value of acceptance. Let me go back and see. All right. Okay, so the I was going to show you the here we go. The peak, this peak of this impedance curve here is defined by this equation. So you can kind of go through the calculations by hand. It is complex numbers, so it's a little bit more difficult to do. But this peak here is defined by a value of x of c squared divided by n, and then divided by the resistance of the network. So in this case, n represents the harmonic resonant point, the peak value. What value of n, what value of harmonic is it? X of c is the 50 hertz or 60 hertz reactance, and R is the resistance of the network. So at resonance, the peak of the impedance curve really defines the possibility of what voltage distortion you can get. The interesting thing to note here is we're at a value of about 600. So even 1 amp of current injection at that harmonic, okay, would result in close to 600 volts. 600 volts line to neutral. So these are single phase calculations. It's a line to neutral voltage value at that value. So 600 volts on a 13.8 system, which normally would be 7,960 volts line to neutral, would represent a very high voltage distortion for just 1 amp of current injection. 1 amp of current at this frequency here would result in about 550 volts. So I can take 550, say 550, 7960 divide, which is the line to neutral voltage at the fundamental, it'd be 6.91%, so just 1 amp of current injection. And 1 amp of current injection at that 5th or near the 5th harmonic is not a lot of current injection. So resonance is something you want to avoid. The resistance of the network is always very low. So at resonance, you're going to get these peak impedance, these peak values in your impedance, which is going to result in high voltage distortion, high current distortion. It's going to amplify the current. So you want to avoid resonant conditions where they can interfere or overlap with harmonic current injection, say at the 5th or at the 7th or at the 11th, those primary harmonic currents that you often see. Okay. Okay, so the next thing to talk about here is that if we were looking at this, we might say that this system is okay. We don't have a 5th resonance. I don't have a 7th resonance. My voltage distortion is at 4.32%. But I look at the impedance curve, And the first thing I know is, well, what if it were to shift to the left? What if it were to shift to the left? I don't have any harmonic current right now at the resonant point here. I'm slightly off to the left. My resonance is slightly to the right of me. I'm okay. But the reality is that we do not know the system good enough oftentimes. We don't know the system good enough. And that the impedance curve could shift. Okay, could shift to the left. In this case, if it were to shift to the left, that current would then be injected times that impedance value of 600 ohms, and we would have a value of 5,127 volts. So 64% voltage distortion, so unacceptable. So what can cause the shift? And a lot of things can cause the shift. We got variable capacitance. Also, capacitor banks are built 0 to plus 10%. We have variable impedance of the source. What local generation do we have? What transmission lines are in and out of service? That can also impact the impedance of the network. And we have motor load within the plant. We all know that as we increase the motor load within the plant, the short circuit impedance goes down, or the short circuit current goes up, and therefore we will get a shift in that impedance curve. So there are a lot of things that can shift the impedance curve. We can have cable capacitance within the network that will also add capacitance to this capacitor here, causing a shift. So when you look at when you do harmonic analysis, you can't just look at the values of voltage and current distortion. You have to take a look at the impedance curves and say, okay, let me do a perturbation on the system. Let me make some changes here. What changes are reasonable, and can I have a resonance concern? Can I have a resonance issue? This is something you got to look at. So that's the importance of the impedance curve, is to look at that curve and say, if I shift left or right, can I run into a resonant condition? Can it overlap one of my dominant harmonics in the network? And so always consider that possibility. The one thing that we often see is that nowadays there's what's called active front-end drives or high pulse drives where the harmonic currents are low. And in the United States, they would say that, well, that's an IEEE 519 compliant drive. It complies with the standard. If it complies with the standard, then I don't need to worry about harmonics. That's what's talked about. So I took some Rockwell Automation drive data, and I said, okay, well, in this situation, if I were to have a 5,000 horsepower drive and I were to connect it to this network, I would have a certain amount of harmonic current times that impedance, and I would get a distortion value that would still be excessive. So and you can do the same for both types of drives here. So the point here is that when you're adding capacitors to the network, even with active front-end drives or high pulse drives, you still need to be concerned about harmonic resonance, because harmonic resonance, even a small value of current injection, even a small amount of distortion, can result in an amplification of that, and it can exceed your limits. You can do the same thing with Yaskawa. Doesn't matter who it is. I've done it with also with Siemens. All of those drives, they put out very low values of distortion. They're great. It means that if you're installing a filter system in your project to avoid resonance, that filter system does not need to be as robust. It can be a smaller filter, but it doesn't remove the requirement that you need to, say, detune your cap bank, which is another way of saying I need a harmonic filter. But you can't install standard capacitors. You often get a concept where people say, I want to tune around resonance. Let me tune around resonance. So we zoomed in on this one. In this case, we zoomed in on that same curve here, and I showed down here. And you can see that in this case, even though my resonance was 5.59, and if somebody was doing some hand calculations using that simple formula, they might say, well, I got 5.59, I'm okay. Or they might say, I'm going to design my system, I'm going to install a capacitor bank that tunes me to the 6. And and I'm going to avoid resonance by tuning my cap bank to the 6. The reality is that doesn't work. And the reason it doesn't work is that resonance has a certain broadness to it. It's pretty broad here. Okay, so even though I'm not over the 5th harmonic, I'm still raising the impedance across a range of harmonics. It's got a width to it. And the width of that impedance curve, the shoulder, the width of it, all right, will vary depending upon the value of R, the resistance of a network. And that's an unknown value to some degree. We all know that we have a feeling for the resistance of a cable per meter. The transform impedance, oftentimes we do not know. It's not on the nameplate, so it's something that is unknown. Because resistance is not known and the impact of harmonics, okay, on skin effect and on proximity effects, we know there's some effect, but it's hard to know exactly how much that is. So the width of that impedance curve is also not known. And of course, you got the possibility of shift due to changing system conditions. So tuning around resonance is something that we would not typically recommend, and we actually don't think it works very well. Depending upon where you are in a network, you have sometimes what's called parallel resonance and series resonance. So looking from the drive here, or that current injection point, into the circuit, we have parallel resonance. This capacitor here is in parallel with that impedance here, causing parallel resonance. And that's that blue dashed line down here. The magenta line, though, is us standing here and looking into the network. In this case, we have both series and parallel resonance. We have the series resonance where we got this transform impedance in series with the capacitor, creating a series impedance, and that represents the low point on this magenta curve. And then we have the source impedance here, which is creating a parallel resonance, and that would be represented by the peak here. So we have both a parallel and series resonance. So I bring this point up because oftentimes, especially in large mine projects or large industrial plants, there's a desire sometimes to put capacitors at each and every load level. Put at each and every load level. So you might put capacitors at 480 volt, at 4160 volt, at the 13.8 kV level. Park the capacitors or the power factor correction as close to the load as you can. That's the concept that is often taught in school, because you then have a reduction in current, a reduction in kVA flow through your network. You have better voltage regulation through the network when you do that. The problem, though, is it makes for the harmonic analysis to be very complicated. In a situation like this, I would have multiple parallel, multiple series circuits, and when we have multi-stage cap banks being used at each and every voltage level, it becomes very complicated. And so we have a recommendation that we would say only do reactive compensation, power factor correction at one voltage level. It simplifies the system to just a few number of cases that you need to do simulation for. When you have a plant full power factor correction capacitors at the low and medium voltage level, you get a much more complex impedance profile, and it changes throughout the day depending upon what capacitors are on, what loads are on. If you have a problem, you're going to have a very difficult time locating it and identifying it. So our recommendation is harmonic, or is the reactive compensation at one load level. Multi-stage cap banks we show here, and in this case we have a 1 megavar, 2, 3, 4, the original values of capacitance that we're putting on. That results in four resonant conditions depending upon how many stages are online. So we overlay, we can overlay our current injection values, and we can see that at this one here, 3.8, my 11th harmonic current injection corresponds to the resonance at the 11th when I have 1 megavar on. So 1 megavar could potentially be a problem. You could also, we've already identified this one over here that with a slight shift in the impedance curve, I might have a problem there. You could say the same here. Slight shift in impedance, I might have a problem. But in this case, you can see that just this one alone, at the 11th, that harmonic current multiplied times the impedance, I get a value of 4,180 volts of voltage distortion, so 55%. So quite a bit of voltage distortion. So multi-stage cap banks, you need to evaluate each and every frequency and you increase your odds of having a resonant condition. So what happens during resonance? One of the things that happens is you get an amplification of voltage distortion. We've been shown that. But you also get an amplification of current. Your harmonic current is amplified. So in this case, at resonance here, you can see that the current is amplified by a factor of 80. So what I did here is I developed, instead of developing an impedance curve, I developed a current amplification curve. It has the same look as the impedance curve, but we're doing current amplification. This will be the harmonic current injection is amplified by this value within the resonant circuit. I'll show that in a moment. So you can see here that the current amplification is quite a bit and is over a wide range. That current amplification is flowing in the capacitors, it's flowing in the source impedance. So if you have a harmonic standard at the point of common coupling that involves harmonic current, you're going to easily exceed the standards if you add capacitors to the network. So oftentimes adding filters is the better thing to do. The other thing is the capacitor current will go up, which means that we may operate diffusers within the capacitor. Here's where the amplification of the current is. I got my current injection here. That 8.3 amps here will flow into this point here. This represents the main bus bars within the plant. We're going to have current amplification within this circuit. This tank circuit is often referred to as a tank circuit. Current amplification will occur there. So we may operate diffusers. We for sure will possibly exceed the standards here if current distortion is a limit that's dictated by the interconnecting utility. Oftentimes we have customers, existing plants, where they're trying to evaluate, does the plant comply with IEEE 519 or the harmonic distortion limits as dictated by the plant. And they will send a measurements person out to take some measurements. Oftentimes they're trying to take measurements because they want to get the current injection here for their model. They want to create this model. So they're trying to figure out, well, what is my current injection? They take measurements and they leave this capacitor bank on. Okay, that's a mistake. That's a mistake. If the capacitor bank is on, the value of current that you're measuring, okay, is not the current injection, it's the amplified value. And it becomes useless. You can't use that in harmonic analysis. So if there's consideration being given to adding capacitors to a network or making changes to the network and you're looking to do a harmonic analysis, the harmonic analysis input is a harmonic injection value. It represents the drive output current, all the nonlinear load current within the plant. What is that value of current that you have? And also, I didn't say it, but these values of current here have phase angles. Each and every nonlinear load will produce a certain amount of harmonic current. That harmonic current has a phase angle associated with it, so those currents don't necessarily add. So taking measurements at this location here is nice because it allows you to capture the summation of the entire plant. What's important is that the capacitor be removed. The capacitor has to be disconnected. 15 minutes with the capacitor disconnected is better than any other measurement you could have. So you ask the plant operator, take the capacitor banks off so you can obtain the proper value of current up at that location. So what about adding capacitors as harmonic filters? And that's what we did here. We added a reactor in front. You can see here this is a metal enclosed harmonic filter system being added to the network. All it is a reactor in series with a capacitor. And that reactor, incidentally, is a value of X of L. And that value of X of L is much lower than the value of X of C. For a typical fifth harmonic filter, the value of X of L is 1 over the tuning point squared. So calculate your value of X of C, divide by 25. That's your fifth harmonic impedance of that reactor. So the reactor is 1/25 of the capacitor, which means that a harmonic filter bank puts out reactive power at the fundamental. The majority of the impedance is capacitive, and therefore it is a reactive power source. So remember, filter banks are installed for 3 reasons. One is reactive compensation. That's the primary reason filters are installed on a network. Number 2 is you want to avoid resonance. You're installing reactive compensation on a network, but I'm trying to avoid resonance. How do I avoid resonance? I put a filter in, or I detune the capacitor bank. Sometimes you talk about these as detuned cat banks. And then the third reason is you want to actually do filtering, and this is also a requirement in a lot of the major projects like mine projects where you have very large non-linear loads. So look at the impedance curve here. We recreated the impedance curve here with this magenta line. We're looking into the network. The red dashed line is that reference line that we started with in this presentation, which is the transformer source impedance line. And we overlaid on top of that the impedance curve of the network with the filter. You can see that through almost the whole entire range, except for below the tuning point, the impedance of the network now is less than that reference line, which means that we have definitely reduced the voltage distortion in the plant. So here we're taking the current injection values here, those values there, we're multiplying it times the impedance along this whole curve, and we come up with a bar chart for voltage distortion. And here you can see the voltage distortion has dropped. The other thing to note is that we pushed the resonant point down below the tuning point. Another benefit of adding capacitors as harmonic filters is that we dictate this point right here. That point is dictated by the tuning point of the filter, and the resonance is always beneath or lower than that tuning point. And it's one of the reasons why filters are always tuned to the lowest frequency first. If I have a standard network, almost always the first harmonic filter that's put in is a fifth harmonic filter. We might have situations, mine projects that might include cycle converters, where we might have some harmonics below the fifth harmonic. In that case, you might see a filter put in at the second harmonic or the third harmonic. Another example would be arc furnace applications. Arc furnace applications, the arc furnace has harmonics at the second, third, fourth, and so on. So there's oftentimes you will see a second harmonic filter. You're doing that because you want your resonant point here to be beneath the first dominant harmonic in the network. So you almost always see a fifth. For multi-stage banks, in this situation we have multiple impedance curves, but you can note that the impedance at the tuning point is always the same, and you can kind of zoom in on that. As we add more filters, we improve our filtering capability, but our resonant point is always beneath our tuning point. We do have a shifting resonant point beneath our filter, and that's something that's sometimes of concern on networks that might, say, have a fourth harmonic. A rectifier, for instance, with some unbalance in the network can put out some fourth harmonic, and that's something of concern. Sometimes we have third harmonics in the network, and this impedance curve could potentially shift back to the third, so something to be concerned about. So multi-tuned filters are often used in complex networks with high harmonic current injection. And again, here we have a 5th, 7th, 11th, and 13th harmonic filter. You can see that I've basically effectively dropped the impedance significantly at those harmonics by putting a filter at each one of those tune frequencies. And the result, if I did that current injection here, is that the VTHD drops off significantly. It's a significant drop in voltage distortion, and it's because of V equals I times R. Okay, I is the current injection. That value remains the same throughout all this analysis. The X value, the X of the network, okay, is decreased because we put filters at each one of these frequencies. So you got your dash reference line here versus the impedance curve of the filter. So a couple more concepts to talk about, and we're getting near the top of the hour. Oftentimes we have a customer who will install a harmonic filter, and I'll say, well, I've installed my harmonic filter, so now I don't need to worry about capacitor banks or capacitance within a network, and it's just certainly not true. Whenever you have a capacitor in a network, I have a resonance. Okay, when I have a filter in a network, I still have a resonance. In this case, I have some cable capacitance here, and I have a filter here with this resonance. So there's two resonant points. This resonance is not a concern because I put in a fifth filter. It pushed that resonance down below. But this one up here is of concern. It could be caused by cable capacitance or because somebody added capacitors to a network. This is an example where somebody put some power factor correction capacitors in the network with a tuned harmonic filter. And here you can see we create an 11th resonance. So because you add a filter to the network, it does not mean you can't add a capacitor to that same network. Okay, so in systems, in particular in systems like this, you see this in renewables, we have this cable capacitance. We would go with a type of filter called C-high pass or high pass filter. It's a damped harmonic filter. So, and that's what we're showing here, incidentally. I've taken a notch filter and I've added that notch filter as a high pass filter, and you can see I can eliminate that resonant peak there by putting a resistor basically across the reactor. So three types of filters commonly used in this system are notch tuned filters, just a reactor in series with a capacitor. We have high pass filters, and what we did was take that same notch filter, we put a resistor across it, and we can change the characteristics of the impedance of the filter, and we can dampen out those resonances that I showed on the previous slide. And then we have what's called C-high pass filters. And in this system, we're adding a second capacitor to the network. That second capacitor, in addition to this reactor, is tuned to the fundamental frequency. What we're doing is we're eliminating the impedance across that resistor, which then eliminates the power losses within the resistor. If I have 0 volts, because X of C equals X of L here at that fundamental frequency, it means I have no losses. It means I can bring my resistor value to a very low value, do I would say high damping of the filter, and flatten out that curve and eliminate those resonance concerns that we pointed out earlier. So we're about ready to complete here. Let me go through a couple other concepts. Here's a notch filter, high pass filter application, and I overlay the two different plots. And I just show what you can do with high pass filters versus notch filters. In this case, the red curve represents the high pass filters, where the notch filter is represented by blue. When you use notch filters, you get these predominant resonant points, okay, between the tuning points. When you use a damped filter, you flatten out those resonant points, but you can also note that at the tuning frequency, we are not filtering as well. And this becomes the art of filter design. How much dampening do I do to reduce resonance, but then also filter harmonics? And this is trial and error. It's a process in your filter design. So I'm going to cut it off here. I have been invited to come back 3 more times to EESA to do presentations. I think the next one is on renewables. We're going to talk about the medical solution, how it's well suited for the renewables industry. In the meantime, you can contact John Ray Smith right there in Australia at AMSC. He's on that first slide. You can also go to our website, www.nepsi.com. On our website, we have lots of information. We have tech notes, we have videos, we have calculators on harmonic filter design. And don't forget, NEPSI also builds metal enclosed capacitor banks. And because we're part of AMSC, we can also supply STATCOM systems and what we call hybrid STATCOM systems, which are a very economical way to get some dynamic VARs and passive VARs in the same system. The two systems work together. Anyways, that's it. I appreciate everybody coming on, and we hope. Oh, one last thing, if you could send some comments back if you can comment on in the chat box area here. What do you think of the YouTube environment? Do you like it? EESA was asking the question, what other platform could be used, and this is the standard platform that we use. Incidentally, the videos are all recorded. The same link can be used to view this video tomorrow, next week, next year. It will be on YouTube until it gets deleted by us. We keep them all online. The other thing is we have done 35 tech talks that are now recorded, from harmonic filter design to switching transients, inrush current, outrush current, you name it, just about everything. So any feedback on for EESA on this environment, I think they would appreciate it. And thanks to EESA for hosting me.